Welcome back, physicists. Today, we are going to draw and interpret motion diagrams and graphs for objects that are moving with changing velocity. So to get started, let's draw a motion diagram for an object that is moving with changing velocity. Okay. So first, I'll sketch out our number line. Okay, and I'll throw down some dots. Let's go. Okay, and let's actually start over here. T equals 0, 1, 2, and t equals 3. Again, we can go through the analysis. First, we would draw our displacement arrows, right? And we can tell that the velocity here is changing because the spacing between consecutive times is changing. In this case, that spacing is getting smaller. So let's go ahead and let's turn this into our chart. So when we have time, position, and change in position, so 0, 1, 2, 3. At 0, we are at 9. At 1, we are at 4. At 2, we are at 1. And at 3, we are at 0. And so our change between consecutive positions, we have -5, -3, and -1. And for us to convert that to velocity, we know that we have to take that change in position and divide it by the time that it took. So we have as our velocities -5 meters per second, -3 meters per second, and -1 meters per second. And if we go back to the diagram, we again see that our velocity and our change in position are parallel to each other. So it still points to the right, although we see that it's decreasing, or by decreasing, we mean that each second that goes by, we are adding 2 meters per second to the previous velocity. And if we want to convert that into acceleration, we know that we then divide that change in velocity by the time that it took. So we get +2 meters per second squared, which if I wanted to add on our motion diagram is actually now pointed in the opposite direction from the displacement, right? This would be the acceleration, which is +2 meters per second squared, right? And as we saw last time, if the acceleration and the velocity are in opposite directions, we are speeding down, we're slowing down. And if they're in the same direction, we are speeding up. But now what I want to do is I want to take this and turn this into a graph. And the way I want to do it is let's start with the acceleration versus time graph and remind ourselves how we can use that to figure out the next graph in the sequence. So I'll start with our acceleration versus time graph. Again, 0, 1, 2 for time. And we are at a value of 2 meters per second squared for all values of time. So if I wanted to write that as a function, I'd say that the acceleration as a function of time is always equal to the starting acceleration, which for our specific example is 2 meters per second squared. All right, next, to figure out the velocity versus time graph, okay, let me mark off 0, 1, 2, and 3 for time. And let's, hold on. And let me extend this Actually, hold on. Let's redraw this. Because I know we're going to have negative velocities. Let me just extend this like so. So I just need negative. So 0, 1, 2, and 3. And let's make this 0, -1, -2, -3, -4, and -5. Now, I know that I need to start at t equals 0 at -5 meters per second. Let's make this blue. And every second that goes by, I need to add 2. So from -5, I go to -3. From -3, I go to -1. And of course, I can connect the lines here, right? And I end up with this straight line here. So again, we know that this equation should be given by the velocity as a function of time is the acceleration times time plus the initial velocity. So v as a function of t equals 2 meters per second squared times t minus 5 meters per second. All right, the last thing I'm going to draw is we need our position as a function of time. So again, I've got 0, 1, 2, and 3 seconds. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, I'm going to look at my graph here, and I'm going to see at 0 seconds, I'm located at 9. Then at 1 second, I'm located at 4. I'm sorry, 1 second, I'm located at 4. At 2 seconds, I'm located at 1. And at 3 seconds, I'm located at 0. And I see that I end up with this curved graph here. Okay. And again, this equation here is the position as a function of time is the initial position plus the initial velocity times t plus 1/2 a t squared. I know that my initial position is 9 meters plus minus -5 meters per second times t plus 1/2 times 2 meters per second squared times t squared. And that is my position as a function of time. Right? And let's remind ourselves how all of these graphs are connected. Right? So to go from the acceleration versus time graph to the velocity versus time graph, we calculate the area under the curve. And then to go from acceleration, velocity versus time to position, you calculate that area again. But if I want to go the other direction, if I start at position versus time and I want to get velocity versus time, I calculate the slope. And if I want to go from velocity versus time to acceleration versus time, I calculate the slope again. Visually, we can also connect the y-intercept, right, where the graph starts vertically, the slope, whether it's initially increasing or decreasing. And for the acceleration, right, so this is separate, we have that the acceleration tells us about the concavity or the curve of the x versus t graph. So this graph is curving upwards. It has positive concavity, and we know that we can anticipate that because the acceleration is a positive number. All right, thanks for watching.